So, I welcome you all to my presentation. My presentation is on oscilloscope. So, we are going to discuss analog and digital oscilloscope in this presentation. So, first thing first. So, what is an oscilloscope? Oscilloscope are an electronic instrument that convert electrical signal into a visible trace on a screen display. In other words, they convert electricity into light. These instruments dynamically graph time-varying electrical signal into two dimensions. On the y-axis or vertical axis of the scope, display voltage is plotted, while time is plotted on the x or horizontal axis. The resultant voltage versus time plot show a picture of input signal and is usually referred to as a waveform. As characteristic of input signal change, you can view continuous dynamic updates of the plotted wave on a scope display. Oscilloscopes are primarily instruments that electrical engineers use to test verify their electronic design. So here is an block diagram of analog cathode ray oscilloscope. So in a cathode ray oscilloscope, there is an electron gun which fires the electron through a process of thermonic emission. So then comes vertical plates which deflects the electron beam into y-axis on a y-axis plane. They are connected to an amplifier or attenuator. Then comes the horizontal plates, which are connected to a trigger system. These plates are responsible of deflecting the electrons on x-axis plane. Then these electrons are fired on a display. The display is usually made up of fluorescent screen. So whenever an electron hits on it, it glows. So in this manner, you can detect any waveform uh, through through the probes. So here is an block diagram of a digital oscilloscope. So at the heart of all digital oscilloscope are the scope's analog to digital converter, also known as ADCs, and acquisition memory. This is essentially the component of the scope that takes waveform pictures. The ADC takes an analog input signal and then converts the analog voltage value at a particular point in time to a digital binary value. This is typically accomplished with 8 bit of vertical resolution in most of today's digital oscilloscope. The attenuator, DC offset, and amplifier block perform pre-scaling on the input signal in order to scale the input signal to be within the fixed dynamic range of ADC. When you adjust the voltage per division knob, this set up the specific voltage divider network in an attenuator block to possibly reduce the amplitude of the input signal and also set the gain of an amplifier. When you adjust the vertical position knob, this changes the DC offset. Again, this is to bring the input signal that may have a specific amount of DC offset to be within the fixed dynamic range of the analog to digital converter. The trigger and time-based block control when and how fast the ADC samples. Trigger signal actually tells the time-based block when to stop through taking acquisition pictures. For example, if the scope has a memory of depth of 1000 point and if the scope have been set up to a trigger at exactly center screen, the time-based block enables the ADC memory block to continuously sample the input or order fill at least half of the memory. When an acquisition cycle has been completed, stored sample in the acquisition memory must then be processed for display. Older digital oscilloscopes simply used the scope CPU system to read the data out of the acquisition memory on sample at time, process the data, and then restore the sample data into a display memory. This was a time-consuming process that sometimes resulted in slow waveform update rates, especially when the processing deep memory record. Many of today's newer digital oscilloscopes use dedicated and custom built digital signal processors to quickly process digital filter and then effectively pipeline the waveform data into a display memory to thereby improve the throughput and waveform update rates. If we look at the oscilloscope performance specification, oscilloscope have many different specifications, but the most important specification of an oscilloscope is its bandwidth. The highest input frequency that a scope can capture and accurately measure is based on the bandwidth specification of the scope. But a scope cannot make accurate measurement on a signals of the same frequency as the bandwidth frequency. All scopes exhibit a low frequency response, typically called a Gaussian response. A Gaussian frequency response closely approximates a single pole low pass filter. You may have plotted a response similar to this in some of your classes. As the frequency of an input signal increases, the scope will begin to attenuate the input signal and then begin to make inaccurate measurements. Frequency at which the sine wave input signal is attenuated by 3 dB is the bandwidth of the scope, but 3 dB of attenuation is equivalent to approximately 30% attenuation based on 20 log V naught divided by Vi formula. Measuring electrical signal on an oscilloscope requires getting the desired signal to be tested into the scope input BNC connector. If you want to measure the output of generator, you would typically connect the output of a generator directly to the input of the oscilloscope using a standard 50 ohm BNC or SMA cable. Well, if you want to measure the characteristic of a signal at a point in your circuit, you would typically achieve this using an oscilloscope probe. There are many different kinds of probe used for different and special purposes such as high frequency application, high voltage application, and current measurement. But the most common type of probe used to test the probe broad range of signal is called a passive 10 to 1 voltage divider probe. Here is an image of an electrical model of a passive 10 to 1 voltage divider probe connected to the input of a scope. The term passive here means that the probe includes no active circuitry such as transistor and amplifier. In other words, the probe consists entirely of passive elements including resistance, capacitance, and inductance. 10 to 1 mean that the probe reduces the amplitude of the input signal by a factor of 10 through means of resistive voltage divider network. The oscilloscope measurement system's input impedance is also typically increased by a factor of 10. Last, note that all the measurement using this type of probe must be performed relative to the ground. In simple words, you should connect the probe input tip to the desired test point, and you must connect the probe ground lead clip to a circuit ground. It is usually in a black color. With this type of probe, you can measure the voltage across two mid-circuit components. This type of differential measurement would require a special differential active probe. Note that you should never attempt to complete a circuit using an oscilloscope probe. For low frequency or DC measurement application, we can significantly simplify the circuit by removing all of the capacitive element shown in the model from the previous slide. What is left is just a 9 megaohm resistor near the probe tip in series with the scope standard 1 megaohm input termination. Using Ohm's law, you can see that the voltage level of the signal at the scope input BNC will then be 1/10 the voltage level at the probe tip. Most of today's scopes have probe attenuation factor that will automatically compensate voltage measurement so that they will be reported relative to the probe tip. If you are ever tasked with selecting and purchasing an oscilloscope, here are some important specifications that you must consider. Although bandwidth is the most important oscilloscope specification, there are others like sample rate, which should be at least 4 times the scope bandwidth, memory depth, which determines the length of waveform that be captured. There are also number of channels to be considered. There are typically 2 channels in an oscilloscope, but 4 channel oscilloscopes are also available. But MSO models add additional logic timing channels of acquisition in order to monitor and test more complex set of digital signals. Waveform update rate is also a factor to consider. Uh, Faster update rates mean faster picture taking, which can improve the scope probability of capturing infrequent events such as glitches. So display quality. So we should consider the size, resolution, and number of level of intensity gradation. Intensity gradation can be an important characteristic of a scope display quality in order to view and make intuitive judgment about the random noise and jitters. Advanced triggering mode is also an important factor to be considered, enables the scope to synchronize on more complex signals such as serial bus signals. So this is an end of my presentation. Thank you very much for listening and see you guys next time. Till next time, Assalamu alaikum.